Okay, on this video we are going to talk about the exact differential equation, which is another method to solve differential equations. But before going to the solution, to the methodology of solution, we need some background information. Okay, now let's start with the definition of exact function. Actually, from here is where the name of the method comes from. Is an exact function. The definition is a function of two or more variables, doesn't matter the number of variables, but at least more than two. That a function of two variables or more that is equal to a constant. For example, here we have a function of two variables equal to a constant, or a function of three variables equal, for example, here 3. Okay, you may see that you haven't seen this before, but actually you have seen it before. For example, let's do one example. For example, x squared plus y squared equal to 9. That is a circle or radius 3, and it is actually a function of two variables, right? Or you can have x squared over 9 minus y squared over let's say 4 equal to 1, and that is an hyperbola. All right, so it's a function of two variables that is equal to a constant. So you have seen this before. For the three variables example, well, it's very similar. A function of three variables equal to a constant could be this: x squared plus y squared plus z squared equal to, let's say, 4. And what happens here is a function of three variables equal to a constant. This represents a sphere in 3 dimensions. All right. Okay, so this is the definition. This will be an equation of this one or this one. For these exact differential equations, we are going to cover only the function of two variables equal to a constant. So that is my first definition. All right. Okay. Second definition. You may remember this. A function of two variables, you can take how many partial derivatives? Well, because it's a function of two variables, you can take the partial of the function respect to x or the partial of the function respect to y. Still, even though you take the partial derivatives, still the functions are function of two variables. Now, what about the second partial derivative? Because here you have two partial derivatives. If you take the second partial derivative, then here you will have second partial derivative of the function respect to x 2 times, and of the function here first respect to x, but then respect to y. And then here, once you take the first derivative here, you can take the second derivative. You have two choices: second derivative of the function of two variables, first respect to y, and then respect to x, or the second partial derivative of the function 2 times respect to y. Okay. So at this level, this is the first partial derivative. And here is the second partial derivative. As you can see here, in the first partial derivative you have 2 partial derivatives. On the second partial derivative you have 4 partial derivatives. Now if you try to make the third partial derivative, then you will have 8 partial derivatives. But let's keep until this level. Okay, now what I want to extract from here and pay attention from here is these two guys. They look different, but they are actually the same. The only difference is that on the one branch you take the partial derivative respect to x and then respect to y. In the other branch you take first respect to y and then respect to x. So they are cross partial derivatives. cross partial derivatives. Now, if the function of two variables is a continuous function, then what happens here is that these two guys happen to be the same. So the second derivative of the function of two variables, first respect to x and then respect to y, you will get the same result if you take the partial respect to first respect to y and then respect to x. So this is the concept number 2 that we are going to keep. Okay, so first concept, function of two variables equal to a constant that is an exact function. And then second concept, the second partial derivatives cross first respect to x and then respect to y is the same as the partial first respect to y and then respect to x. So that is the concept number 2. Let me check if I can have the concept number 3 here. I don't have much space, but let's try it. Concept number 3 is the following concept. When you, here is the differentials. What is the difference between differentials and derivatives? Well, here it's just a concept, but in the formulas they are the same. For example, let's say that you have y as a function of x, and you take the derivative of y respect to x, so that is f prime of x. So it's the derivative on both sides. So this is the derivative, but the differential will be differential of y equal to f prime of x, differential of x. So that is the only difference. You just take the differential of x to the other side, and then you get the differential. So here is the derivative, and here is the differential. Okay? So the differential is just the differential of y is the function, the derivative of the function times the differential of x. So this is when the function is of one variable. But what happens when you have the function of two variables? Let's say zeta equal to the function of two variables. How do you calculate the differential of zeta? Okay, because you have two variables, then it's going to be very similar to this, but this is a function of one variable. Because this is function of two variables, the differential of zeta will be partial of f respect to x times differential of x plus the partial of the function respect to y and then differential of y. So that's how you get the differential. So the differential on two variables is the partial respect to x times the differential of x plus the partial of the function respect to y and then times differential of y. Now if you happen to have three variables, if this is from three variables, then you just add the partial of the third variable, differential of the third variable. But let's keep for the two variables. Okay, now this is concept number 3. With concept number 1, then what if this function of two variables is an exact function? What if this is equal to a constant? What will be the differential of a constant? The differential of a constant will be 0. So if this happens to be a function of an exact function, then the differential of the exact function will be something like this. The partial of the function respect to x times differential of x plus the partial of the function respect to y times differential of y, and this is equal to 0. Y is equal to 0 because the differential of a constant is equal to 0. It's just a constant minus the same constant is equal to 0. So this is concept number 3. Alright? Okay, engineers. So we are going to use these three concepts to make the definition of the exact differential equation. By the way, this is actually the exact differential equation. So this is the exact differential equation. On the next video, we are going to cover how to define the exact differential equation, which is that, how to check if it is exact, and how to solve it. All right. But these are the concepts that we are going to need. All right. See you in the next video.